6, we're going to rework back through pretty much all of the material that we have learned so far, but apply it in a new way to this idea of rotation rather than translation. Translation is what we have been looking at throughout the entire semester so far. So we kind of learned that objects have a mass, right? And we call that mass the inertia, which is their resistance to motion. But if I were to apply a net force to an object, it would cause that object to accelerate relative to its mass. So the force to mass ratio causes the acceleration. Then we've said in the last unit, unit 5, we started saying, okay, well, if I apply a force and I move something a certain distance, that's called work, which is also called the change in energy. I have added energy to that object, right? Whether it's kinetic energy and it's increasing its velocity, or it's gravitational potential energy and I have picked it up off the ground and moved it directly upwards, right? So these concepts are all going to apply to also the idea of rotation. So when we've been talking about these forces that we're applying to any objects, is a push or a pull on the object. And always when we've been drawing our free body diagrams, we just draw a little box and we draw a little arrow, right? And we assume, like, if I push with this arrow, it's just going to make it go straight and align this direction. So we sort of taken for granted the fact that every single object that we're pushing causes it just to go straight forward. So if I were to push this object, I would cause it to accelerate straight upward, sort of, right? Now, really why it moves upwards and why I'm having a little bit of trouble getting it to go is that I am pushing at the center of the object, right? Which is really called the center of mass of the object. Let me just cheat. And it will make it go that way. However, if I apply that force anywhere outside of the center, like the direct center of the object, look what happens. The object rotates, right? It rotates around its center. So, an object that's wanting to rotate also has a mass of sorts. We actually call this the rotational inertia, or the moment of inertia, right, which is written with this letter I. And that really is about how that object distributes its mass about what is called the center of mass. Right? And the center of mass is really the place right in the middle where it's evenly distributed, all of the mass around the outside of it. And we'll be dealing with pretty uniform objects, so it'll be pretty easy to tell where the center of mass of things are. And it's where, if I were to apply a force, that object would translate rather than rotate. Okay? And we'll do a couple of activities with this idea of center of mass. All right, so if I apply a force then outside of the center of mass, then it's going to cause the object to rotate about the center of mass, right? This is actually an idea called torque, right? And we'll look at the equation for torque later, but I just wanted to kind of get the terminology for you here now. So if I apply a force some distance away from the center of mass, or let's say there was a fixed point, right, where the object can't move, then this object is actually going to accelerate, just like Newton's law says, and it's going to have a what is called angular acceleration. So this is angular acceleration, right? Now, relative to its mass, well, not just its mass, but what we are calling its mass, which is its distribution of mass, which is rotational inertia. So see how these equations are the same. Force is torque when we're talking about things rotating. Mass is your rotational inertia, or your distribution of your mass. And then acceleration, this is the angular acceleration, or how you're accelerating relative to the radius, right? Now, if I apply a net force, right, then this thing should angularly accelerate. If there's no net force, then the object, or if there's no net torques, really the object should be in equilibrium, right? So it should either be in static equilibrium or going at constant velocity. So if I apply, say, a torque right here, and it goes at constant velocity, really the torque that's acting backwards on this object to make it go a constant velocity is going to be the friction, right? Otherwise, this thing should start to accelerate and spin around faster and faster and faster. So, if I have done work on this object, right, so I'm applying force and I'm causing it to accelerate and go faster and faster and faster, then through this torque, I have actually added energy to the object, and we still call this work, but it's torque, right, which is like sort of substituting in for force. And when we're talking about motion around in a circle, we actually say it's per degrees, right? This is just an angular way of saying it, right? And if it's speeding up and going faster and faster and faster, I have then changed its energy. And the way that I'm changing its energy is making it speed up faster and faster and faster. This is what we call the rotational kinetic energy, right? And we will look at the equations for these things, but I just want you to see sort of this idea, these concepts right now, and then we'll go into more depth later. So mass is inertia. When we rotate, it's your rotational inertia. The center of mass is right at the center of the object, where if we applied a force, the object would translate. But if we apply the force anywhere outside of the center of mass or some point that is fixed, then the object will rotate. That force applied some distance away from the center of mass or a point of rotation, instead of being called just a force, is actually a torque, which we'll look at later, which, according to Newton's second law, will cause an object with a certain rotational inertia to have an angular acceleration. If we're applying a force, a torque of sorts, some distance away from a center of mass, and the angle changes, then we are changing the rotational kinetic energy. All right, so this is sort of a big picture of everything that's sort of going on in this entire unit, and now I'm going to kind of go in and tear it down and break into the little pieces and see how we can quantify these things.